Hey, welcome back. Modern Algebra Made Easy. I'm Scott Hader. Today we're going to be talking about direct products and finitely generated abelian groups. And this lecture is really, wow, it's a big lecture. I'm going to try to keep it under 30 minutes. Stay tuned to the end because there's something that I think is really important that I try to give an explanation for that, as far as I can tell, is not anywhere else. It's not profound, but it's not given anywhere. So here's a review on direct products, what they basically look like. What you probably used to, maybe in your discrete math course or something like that. Direct products they look like a point. For instance, x and y, where x and y are in the reals. It's a point, right? But what may be new to you is seeing them like this. And this is like, maybe you've taken multivariable calculus. Basically, these are components. So we have I number of components, and each of them come from their corresponding set here. So each of them come from a set. Alright, and if each of these components is from a group, then together it forms a group. And I'll give a proof later. In other words, each of these are groups individually, but together as well it's also a group. So finitely generated abelian groups. So that's direct products. Now finitely generated abelian groups. If you don't know what this means by now, it's totally okay, because neither did I. I had to look up a lot of stuff for this lecture, and it took me a lot of time to make. So finitely generated abelian groups. It's abelian groups with finite generators, as far as I can tell. So basically, these are two examples. The integers and the integers mod n, these are both generated by 1, or negative 1 as well. However, the reals and the rationals don't have generators. There's no number that you can keep adding or subtracting and generate the whole reals, all the reals, or all the rationals. Like you take a small fraction, well, there's always a smaller fraction, and so forth. And a really important piece of information here is when we're talking about groups, we're talking about addition as the operation here. So why are we not using multiplication? I'll answer that in just a second. Remember, addition is always abelian. So abelian is also used for kind of the notation. A plus symbol is kind of symbol for. It's kind of the notation for an abelian group. So why don't we use multiplication? Well, if you'll notice, these two groups right here, actually they're not groups under multiplication. Did you realize that? Because I didn't until like a day ago. Alright, they are not groups, unless you exclude 0. And they're also not that interesting under multiplication. They're more interesting under addition. So, but anyways, the point is that we're talking about abelian groups, so we're going to use addition as our operation. So we're going to be dealing with things that look like this. We're going to have direct products of congruence classes. Could have several components. So for instance, Z2 cross Z3, you have Z2 is the set 0 and 1. Z3, 0, 1, and 2. So together, every combination, you have 2 choices for the first and 3 for the second. That's 6 total combinations. So we have 6 elements in the group Z2 cross Z3. Is there a generator for this group? What do you think? 1, 1 generates it. And here is proof. This is equal to our group. Just 1, 1 plus 1, 1 is 0, 2. 0, 2 plus 1, 1 is 1, 0, and so forth. So 1, 1 generates this. There's also another generator. Can you find it? By the way, since it has a generator, it's cyclic. Two tips. Order of a group that is a direct product is you just need to multiply their subscripts. Always. Always, always. So, for instance, we had 2 and 3 here, the previous one. So we just multiply 2 and 3, that's 6. So we could have known just immediately. That's 6. So, is it cyclic? What do you think? Do you think this group is always cyclic? It's only cyclic if and only if n and m are relatively prime. So these two numbers have to be relatively prime. So before we found that z2 and cross z3 was a cyclic group because we found a generator. Also, they're relatively prime. So it seems like I'm saying the same thing over and over, but really I am. Okay. So find the order of each element and of the direct product. So 2, 6 in z4, z12. So how do we find the order? That means we basically add it to itself. We keep adding it to each element until we get the identity. So 2, 6 plus 2, 6 turns out to be 0, 0 when you mod it by z4 cross z12. So 2, 6 generates the cyclic subgroup with the identity and 2, 6. So it said find the order. Order's 2, since there's 2 elements. Alright, so 2, 3 in z6 cross z15. If you take 2, 3, add it to itself, you get 4, 6, and so forth. You get 15 elements total. And now notice there's 90 elements in the group z6 cross z15 when you multiply these two. And pulling from a previous lecture on Lagrange's theorem, which you'll probably see over and over, when we divide the two, we get 6. So there's 6, the index is 6. It would take 6 cosets of 2, 3 to partition this whole group. Find the largest order of all cyclic subgroups of z6 cross z8. So first we got to find the cyclic subgroups of z6 cross z8. So first we got to find the subgroups of z6 cross z8. So notice there's 48 total elements in the group. And now the subgroups are basically just the subgroups of each component. So the subgroups of z6 are z6, z3, z2, and the set with 0 in it. Remember, just all the numbers that divide into 6. And z8 is 8, z8, z4, z2, and the set with 0 in it. So basically, we're just going to rearrange all the ways you can write those subgroups. And turns out there's 16 of them, because we have 4 subgroups of z6 and 4 subgroups of z8. 4 times 4, that's 16. So now can you find which of these groups are cyclic? Now I'll give you a hint. One of the rows, they're all cyclic. The others are not. And I hope you were thinking it was line 2. Notice these are all relatively prime to each other. So they're cyclic. And now what are their orders? 12, 24, and 6. So the largest is 24. So this is the largest order. The largest ordered cyclic subgroup of z6 cross z8. Gosh, this stuff, you just can't get around talking for years before you get out what you're trying to say. Alright, so fundamental theorem of finitely generated abelian groups. Here's the formal definition. Every finitely generated abelian group is isomorphic to a direct product of cyclic groups in the form of this. Now, this basically is z modded with some prime to some power. The base just needs to be prime. the number, this result doesn't have to be prime. For instance, 2 to the third would be 8. So together it's a composite number, but it's a prime to some power. So I'm going to give a sort of a deeper explanation as we go along, but I kind of need you to just go with me a little bit here. It's not going to make 100% sense right away. And the whole form is this right here, but you can ignore the forest green for right now because, well, it's not pertinent to this lecture. So, some things to keep in mind: these primes could be the same. We could use 2 in different instances. We could even use them to the same power. But we cannot have composite numbers with different primes. In other words, we wouldn't use like Z6 because 6 has 2 different primes in it. Again, it's going to mean nothing to you until we do some examples. I hate giving definitions before we do examples, but had to do it that instance. So, because you just have absolutely no idea how to do this if I didn't. So, find all abelian groups up to isomorphism of order 8. So, basically we're just rearranging the way we can write primes to some power. So 8 is, first we prime factorize it, it's 2 to the third, and we can rewrite that as 2 to the second times 2, or 2 times 2 times 2. So this corresponds to 3 different groups: Z8, Z4 cross Z2, and Z2 cross Z2 cross Z2. Notice all of these groups are order 8, as specified. We just rearranged the way we wrote those primes, and those are our new subscripts. And that will make more and more sense as it goes along, I swear to you. So find all abelian groups up to isomorphism of order 720. Step 1, and don't worry about up to isomorphism, don't worry about that term, we're going to get to it. Right now I just want you to focus on working the problem. So first we got to prime factorize 720. We can write it like this. And now that corresponds to 16, 9, and 5. So here's our first group. And now if we write 3 squared into 3 times 3, we have another group. See how we're just making different groups by rewriting the subscripts? And notice, well, I'll tell you at the end here. So here's the rest of the groups. If you want to pause it and look at them all at once, that's fine. If not, that's fine too. But you should notice that the order of all of these, the order of each of these, I should say, is 720. So we get the order by multiplying these subscripts here. Because there's 2 elements here, 2 elements here, 2 elements here. To find all the combinations, you need to multiply all these together. So they all have the same order. Why do we write these like this? Well, they have different structures. And to understand what that means, you're going to have to wait till the end so I can give a little better explanation. But at least know how to do that problem. At least know how to get the answer. First step. Now, earlier I said that if each component is in a group, then the whole thing forms a group. And now we have proof. And so the first step in showing that something as a group is we got to show that it's closed, right? So we got to take 2 elements in our group and show that when we start together, we get an element that's also in the set. Right now it's a set. We're proving that it's a group. So we take 2 elements in this set. This whole thing forms a set. And when we star them together, and by the way, we're talking about products. These are direct products. So our operation is multiplication. And the way we do multiplication for direct products is by components. So when we compute this product, we multiply the components. And now, each of these components, let's just go to the next little bullet here. Because G is a group, each product is in each group respectively. So A1, B1 is going to be in G1. Because first of all, A1 and B2 come from G1. A1 and B1 come from G1. And since they are in a group, then since the group is closed, when you multiply them together, you get another element that's in the group. So what I'm trying to say is each of these is in each of these. So these products are in each of these respectively. So the whole thing is closed. The product is closed. So I hope that makes sense. If it doesn't, let me know. So that's for closed. And now for associativity, just remember this is the basic format for showing something is associative. And so we need 3 elements though to prove something is associative. So we take a third element. So this is an element, and it's in this set that we're trying to show as a group, which is a direct product of groups. And when we start with the left-hand side here, we should get the right-hand side. So we start with the left-hand side. We can compute this product here by multiplying each component. And now we can multiply each component here. Remember, we got to keep the order straight. A1, B1 times C1. So now we know that A1, B1, and C1 are in group 1. And since we know this is a group, we know it's associative. So we can rewrite this. We can regroup it. Since we know group 1 is associative, we know these components are associative. And since we know group 2 is associative, we know the components of group 2 are associative. And it works for every component. And so since we know that, now we can break this up. And now we can break the second component, the second element up. And now that's the right-hand side of the equation. So we showed that the left hand equals the right hand. So that's associativity. Now we need to show that the group has an identity, or the set has an identity. Well, we're saying that that identity, that element, is this right here, the set of components. In other words, it's each element, it's each identity for each group, component-wise. And when we multiply that times an element in our set, again, we do it by components. And since in group 1, the identity in group 1 times a component in group 1 is just going to be that component in group 1. So here's the left side of our equation, and here's the right side of our equation. And to show that each element has an inverse, we got to multiply an element times its inverse. And I'm claiming that basically that inverse is each inverse of each group. Like, in other words, you take an element in A1 in group 1, and the inverse of that element in group 1 is the first component, and so forth. And now when we multiply this together, again, we do multiplication by components, and that just turns out to be the element, the identity in the first group, and then the second component is the identity in the second group, and so forth. So that's all 4 parts to the showing that that's a group. So we're good. I forgot about the check mark. But anyway, it's time for concept time. This is really the exciting part of the lecture. The other stuff is just building to this. We're getting to the more interesting part, kind of the meat of the issue. I'm vegetarian, but just using metaphors here, so it's okay. So take a group with 18 elements, and I made a mistake here. It's supposed to be an abelian finitely generated group. A finitely generated abelian group, not just a group. But it will be isomorphic to an arrangement of primes of some power, just like we did before. So that means that the only way that you can, when you factorize 18, that's 3 squared times 2, right? The only way you can write those as primes of some power are 9 times 2 or 3 times 3 times 2. So these are the 2 group structures that we have. And it's yay time. We're still building here. Here's the question that bugged me for about 48 hours. It was in the back of my mind. I was thinking, what about this? No. What about this? Yeah. Wait, no. Just back and forth for like 2 days, I swear. I just couldn't wrap my mind around, like, why don't we write Z18 or Z6 cross Z3? Notice these are also order 18. But these aren't prime to a power. But still, those aren't prime to a power, but why don't we write them? I mean, what's so special about primes to a power that we don't have with, composites to some power? Well, do you have an answer? It's because these are guaranteed to have the same structure as an arrangement of primes of some power, and we don't want to be redundant. So this word structure, I'm going to explain a little bit more about what I think that means. I'm 100% convinced, but I couldn't get any validation from the internet or my book or anything like that. So it's basically just my understanding of what it means to have the same structure. So let me try to show you what that means, in my opinion. So I hope you're thinking. I hope you're curious also. I hope you have that curiosity. Like, because if you look online, what does it mean for 2 groups to have the same structure? Like, that's so vague. What is it talking about? I mean, surely there's some explanation. Well, here's my explanation. I'm going to claim that Z9 cross Z2 has the same structure as Z18. That's why we don't need to write Z18. And I'm also going to claim that Z3 cross Z2 has the same structure as Z6 cross Z3. And here's the reason why. But I'm going to ask you to do something. Do yourself a favor. Do it. Because I did the legwork to prove it to myself. Now I'm going to ask you to do the legwork to prove it to yourself. Write out the number of generators for Z9 cross Z2. Go ahead. There's 18 elements in Z9 cross Z2. 0, 0, 0, 1, 0, 2, sorry, not 0, 2, 1, 0, 1, 1, 2, 0, 2, 1, and so forth. So there's 18 elements, and there's 18 elements in Z18. 0, 1, 2, 3, all the way up to 18. Find the order of all of those elements, and find the number of generators, and find the order of each element. You will find that Z9 cross Z2 and Z18 both have 6 generators, and furthermore, they all have, they have 6, 6, 2, 2, 1 elements of orders 18, 9, 6, 3, 2, and 1 respectively. What this means is they have 6 elements of order 18, 6 elements of order 9, and so forth. 6 elements of order 18, that means they have 6 generators. Right? 6 elements of order 18, that means they have 6 elements that generate a subgroup of order 18, which is the size of a group, which means it's a generator. So if you do all that out, you'll find that they both have the same number of elements of each order. It's really interesting. I can't tell you. It's really interesting to me. But I think you should try the second one on your own. If you didn't try the first one on your own, you should try the second one. So you should write out the number of elements in Z3 cross Z3 cross Z2, and they look like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 2, 0, 0, 2, 1, and so forth. You should write out all the elements of 6 cross 3. So 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and so forth. And find the order of each of those elements. In other words, find how many times you need to add each element to itself to get the identity. And you will find that they are equal. They have the same number of elements of each order. And it is not the same as the top bullet. These two structures are different. In other words, they have different number of generators, and they have a different number of elements of each of their orders. But I really think you should verify that for yourself. And it would just take another 10 minutes to explain that on another slide, and I just don't think it's helpful for me to do it. And so basically I'm just going to summarize this fundamental theorem of finitely generated abelian groups. It's basically saying to, well, I'm going to say that at the end actually. So to get a different structure, you have to break up primes. You have to break up you have to break up primes to some power. In other words, Z4, that's Z2 cross Z2. So we broke up a prime to some power. You cannot get the same structure, or sorry, if you break up non-primes, you get the same structure. So Z6 is the same thing as Z2 cross Z3. Because first of all, 6 is composite, but also it's not a prime to some power. So I put non-primes here because it can be composite, it just can't be a prime to some power. So hope that makes sense. So this is kind of an expansion off the first bullet. If you break up a prime to some power, the old group is not isomorphic to the new one. So this is what I said on the first bullet. If you take Z4 and you break that into Z2 cross Z2, they have the same order, but they are not isomorphic to one another. Those are two different groups. They have two different structures. For instance, Z4 is a cyclic group. It has a generator. 1 and 3 both generate the group. Z2 cross Z2 is not cyclic. No generator. And so when we use the term not isomorphic, or first of all, I should just say, when we use the term isomorphic, that you can identify this word with meaning basically the same or identical structure, these types of things. And from what I can tell in my limited time in math, isomorphic is a very strong word to use. So on the fourth bullet, we have kind of expansion on the second, I believe. If you break up a composite into primes, the old group is isomorphic to the new one. So, like Z6, if you break that into two primes, Z2 cross Z3, that is isomorphic to the new one. So Z6 is isomorphic to Z2 cross Z3. Z6 is isomorphic. It's it's the same structure as Z2 cross Z3. And lastly, finally, this word this phrase up to isomorphism drives me crazy, or it used to at least, because people just throw it around. It seems like people will just, of course, up to isomorphism. I'm not saying that about my professors or anything, or about anyone in particular. It just seems like people, they just tend to say that without understanding what it really means. And my understanding is that it means, isomorphic means the same structure, or basically identical, and for intents and purposes. And this phrase, find all groups up to isomorphism, means basically find all the different structures. Don't repeat any of them, but find all the different structures such that any other group is going to be isomorphic to one of those structures. So we're going to write out all the different structures so that even if you could create a different one, it doesn't matter because it's isomorphic to one of the ones that we've listed. And remember, what we're talking about groups being isomorphic to one another, we're talking about this topic, which is finitely generated abelian groups. So that only applies to those. And what do we mean by finitely generated abelian groups? They're always in the form, or isomorphic to the form, Z sub n. We're talking about groups under addition, remember that. And addition means abelian, remember that. Addition is always abelian and has a finite generator. And that is all for today. Thank you very much for watching. I hope you got something out of it. If you're still unclear about something, please let me know. Please, because there's a lot of things to cover and a lot of details. This class is all about details, isn't it? So if I miss something, please let me know. If there's something you'd like me to elaborate on, perhaps I can make a video response. So anyway, that's all for today. Thanks.